systems. And I suppose kernels mean different things to different people. So kernels in this context is more of the flavor used in machine learning, meaning notions of similarity between measures of similarity between pairs of data. And the objective here is to design kernels which empirically incorporate information about the underlying dynamical system that is generating the data. So I apologize that there will be no mention of Bayes' theorem in this talk. But maybe I will try to. So okay, so this is the plan. So I will start by saying a few words about the background and motivation of this work, including some prior work that was done in this area, and then I will move on to discuss this is the main part of the talk, this so-called cone kernels. So this is a family of kernels that try to, with time-ordered samples, bring in the dynamical vector field which is generating the data through finite difference approximations. And by doing that, as we will see, you can control effectively the geometry that this kernel induces to the data. So with a kernel, we can associate a diffusion operator, and to that diffusion operator, by extension, we can associate a Riemannian metric that is induced on the data set. And the goal here is that basically to control the geometry that the data set gets assigned to fill, in some sense, hopefully we'll make more precise later, to fill the dynamics. So we want to create diffusion operators that know about the underlying dynamics. So I will illustrate this with two applications, one with analytically solvable dynamical systems on a low-dimensional manifold that, however, we can draw pictures of, so we can see intuitively how these objects behave. So there, basically the main conclusion to foreshadow it is that the diffusions operators that we construct have the property that they generate diffusions along the integral curves of the vector field on the phase space manifold which is generating the data. So in this regard, they are adapted to the dynamics. And one could use this for various purposes, this type of kernels. Here I will be focusing more in using them as convolution filters to extract patterns from data, and in this part of the talk, time permitting, I will show some results from climate model data. So before I begin, I would like to acknowledge discussions with a number of people, in particular Tyrus Berry, who is a postdoc at NC State working with John Harlim, my student Mitch Bushuk, and Andy Maida. Okay, so to begin with, kind of like a heuristic picture of what we're trying to do here is that we have a sequence of observations of which are being generated from a dynamical system, and we would like to break them up into a set of modes or pattern such that each of these patterns tells us something meaningful or interesting about the signal. So we are in this data exploratory framework that Eric mentioned yesterday, that this data can be potentially very large and the ambient space can be of very, very high dimension. So just looking and seeing won't necessarily work. So we want to use algorithms to help to guide us into the interesting parts of the data. And just to give an illustration from the atmosphere science, so this is a picture acquired from satellites, which measures the infrared brightness temperature of emission from the surface of the Earth. So this is a good proxy for deep convection. So you see here these deep convective clouds around the equator, and these organize in various ways. And so embedded in this signal, so this is an image from 1992, but there is a satellite record that spans at least 3 decades. So embedded in this type of signals, there are various processes of interest to climate scientists. I'm listing here a few, and these span multiple scales in space and time. So what we would like is that we are able to extract these from the raw data doing minimal kind of pre-processing. We want to let the data speak for itself. So a standard procedure of doing this, just to set the framework here, is the well-known method of principal components analysis, which one way of thinking of it is that we can collect our data in a matrix and form the empirical spatial and temporal covariance matrix, compute their eigenvectors, and we can think of each of these of decomposing our original signal into a set of patterns which are given by convolving our original raw signal with the eigenvectors, in this case of the temporal covariance matrix. Or we can think of them as doing a singular value decomposition, essentially, of our data. So geometrically, what this procedure is doing is taking is using these temporal patterns, these eigenvectors of the temporal covariance matrix, as to create convolution filters which are given by linearly projecting the data onto the spatial pattern. These are in the climate science community, those are referred to as empirical orthogonal functions, or EOFs. So however, this procedure is not necessarily well adapted to dynamical system data. Here I'm listing two reasons. One is that this algorithm, when presented with this cloud of points, doesn't use information about the time ordering of the points, and we believe that there is meaningful information there. So we could reshuffle our data arbitrarily in time. We will get the same results if we do classical PCA. The other potential shortcoming, which has been demonstrated in various contexts in the literature, including work by Dan and Andy, is that the patterns that arise from PCAs, these empirical orthogonal patterns, are not necessarily the dynamically significant ones, even though they optimally capture variance of the signal. And here in this context, dynamical significance usually refers to creating, Galerkin type reduced models from the EOF basis, where it has been documented that you can explain 99.9% of the variance with the EOFs, but the reduced Galerkin model will perform very poorly. So one, there are many ways, obviously, of modifying this procedure to incorporate dynamical information, but a classical way of doing that dates back to works of Takens and Sauer et al., which basically propose the so-called delay coordinate procedure, which says that instead of looking at individual snapshots of a dynamical system, as observations of a dynamical system of our data, we are going to create these small sequences of observations, in other words, some spatiotemporal movies, and call these our data vectors. So effectively what we're doing is we're embedding our original data in a higher dimensional space and doing whatever data analysis we wish to do in that space. So one important point to make here is that by doing that procedure, effectively we are encoding information about the dynamics into the geometry of the data. So what I mean by that is that if we measure the distance between two states in delay coordinate space, that distance depends not only on a single, on a single pair of snapshots, but rather on short histories of snapshots. And the particular histories, of course, depend on the underlying dynamical system. So in this regard, if we do, say, PCA in this space, the results will no longer be invariant under arbitrary reshuffling of the snapshots, because we will have created these embedded vectors, and we have committed ourselves to this particular sequence that we visited the snapshots. So the conceptual picture that we have here, and is kind of like motivating the use of kernels, is that these short sequences of observations lie on a low-dimensional set, which typically is considered to be a manifold in our delay coordinate space. And we can think of there is an embedding function which, given a point on this manifold, gives us this sequence. So that manifold has a Riemannian metric induced on it through this embedding, and that Riemannian metric will depend on not just the observation function we have, but also the actual dynamics. So we would like to use that to use techniques which were developed originally in machine learning, in particular kernels, to access that geometry. So the way that this is typically done is to introduce a exponentially decaying kernel. So this is a function that takes a pair of states on this manifold and returns a positive number, which decays exponentially fast away from a given base point. So if we fix AI here and call it our base point, and we can performing various effectively rescalings or normalizations of this kernel. So what I'm showing here is that starting from our kernel, we can define an integral operator, and so I forgot here.
Dimitris,
Yes.
What's the relationship between AI, XI?
Oh, I'm sorry. Yes. So yeah. So AI is the abstract point on the manifold, and XI is applying this embedding function to get that point.
XI lives in Euclidean space and AI on the manifold.
Yes.
I just had to know which one was met.
Right. So sorry, I forgot here to include one additional step, namely, we take our kernel and we form a integral operator which takes functions, maps functions to functions on that manifold. So this is a averaging operator, and then if we normalize it, we can turn that into a transition probability. Sorry. I will come back to this with more specific details later on in the talk. But if we can normalize this G operator suitably to an averaging operator, meaning that an operator that preserves constant functions on our manifold, and from that we can construct a diffusion operator. So this is analogous to a Laplacian, and associated with this operator is a Riemannian metric. So there's a usual div grad formula. So in this sense, starting from a Gaussian kernel, we are inducing a geometry on our dataset through the corresponding diffusion operator. And there's another typo in this slide. This L should be delta. Sorry for that.
Delta is the Laplace-Beltrami.
Yes, delta is the Laplace-Beltrami associated with the metric on on the in this delay coordinate embedding space.
Quick question. When you talk about the delay, when you talk about the embedding, so you do assume that the system you're looking at has an attractor. Right?
Yes. Yes. So this is more like a motivation. In fact, in the next part of the talk, I'm not going to use delay coordinate embedding. I'm just saying how one way of changing the geometry of the data in a way that depends on the dynamics. So in general, and this was a nice place to read, that is the PhD thesis by Tyrus Berry. We can draw a correspondence between the induced metric on the dataset and the kernel through its Hessian. So it turns out that if we look at points which are in an exponential neighborhood around our base point on the manifold, and we take derivatives of this of our kernel with respect to these exponential coordinates, then these derivatives are proportional to the metric that gets induced on the manifold by a given kernel. So this motivates that we can control motivates the fact that we can control the geometry on our data by appropriate choices of k. So in this case, we had an isotropic Gaussian kernel, and that led to basically the Laplace-Beltrami operator associated with the embedding of our manifold in delay coordinate space. But in general, we could work with other kernels and create different metrics to suit our particular task. And what was developed in the machine learning and harmonic analysis literatures, these are the well-known papers of Belkin and Nayogi, Koifman and Lafon cited here, is that the corresponding diffusion operators, so this object here, can be estimated empirically from discretely sampled data. So these are standard algorithms that have been used in machine learning for some time. Here we want to create kernels that allow us to extract information or to control the geometry of the data depending on the dynamics, and use these algorithms to work with practical data.
By estimating it, you mean finding the metric?
By estimating it, I mean finding a discrete analog of this operator, so a discrete analog of this object that, if you have infinite samples, it converges to this.
To delta?
To delta, yes. So basically you have a discrete diffusion operator. I will show in a moment the steps to compute that. And under certain conditions, that discrete diffusion operator will converge to the continuous one. So what was done in our earlier work with Andy, and also in independent work by Tyrus and his collaborators, is to use these kernels for the machine learning algorithms in this Takens delay coordinate space context, and basically the procedure is to replace the covariance operator that was used in PCA with eigenfunctions of this diffusion operator that we obtain in our delay coordinate space. So I keep making the same type all the time. So here, I guess I mean here I would like to replace this by delta, but so the point is that instead of looking at covariance eigenfunctions, we're going to look at diffusion eigenfunctions and use these as convolution filters to extract patterns from our data. So these are not going to be patterns that necessarily explain optimally the variance, but the hope, and this was discussed in a more theoretical way than in our work with Andy, the hope is that these patterns are are going to be dynamically significant because of the fact that the geometry in the delay coordinate space depends on the dynamical system. So, for example, we tried this procedure in the case of the Charny-Devore model of Dan, and we found that the using these as basis functions for Galerkin truncation leads to superior performance compared to using standard EOF. So they had better performance in Galerkin reduced models. However, the problem, one of the let's say difficulties with this approach is that actually getting a handle of the metric that the data acquires in this delay coordinate space is highly non-trivial, because the dependence on the dynamical system only happens indirectly through the time delay coordinate procedure. So in this talk, so for the rest of this talk, I would like to consider kernels that have a dependence that on the dynamics which is explicit. So I will show in a moment what I mean by that. So instead of having an isotropic Gaussian kernel and having the dynamics enter through these embedded delay coordinate embedded vectors, we want to empirically introduce some information about the underlying vector field in the formula for the kernel. But the general approach remains the same, namely we want to bias the geometry of the data through the dynamics. Okay, so the setup here is similar to what we've seen, I guess, earlier today and also yesterday. We have a deterministic flow operating on an attractor, and we take observations at a time step delta t, and these observations are through a vector valued function which takes a point on this manifold to a Euclidean space, to a vector space. And on this manifold we have some nowhere vanishing vector field which is associated with our flow, and the assumption that will be made here throughout is that the observation map is an embedding, namely and in particular that the derivative of this map is has full rank on is invertible and has full rank on the tangent spaces of the manifold. So we can think of we can take our dynamical vector field and push it forward to observation space, and so effectively that induces a metric on our manifold by pulling back the associated the inner product of our data space. So this is our general framework. Now what we're going to do is we're going to create finite difference approximations of this object here by our time ordered data. So what do I mean by that? I mean that if we have a sequence of have a timestamp to each of our observations, and we have a finite difference operator of some order of accuracy. So in this cartoon sketch, I'm showing a backward difference scheme of accuracy 1, namely for at sample xi, we compute the difference between that and in its temporal neighborhood in the past. So that gives us another vector xi, and that vector is a first, in this case, is a first order accurate approximation to the push forward of our dynamical vector field in data space. So this is something that one can check straightforwardly. But the point is that this object, this xi, we can evaluate it empirically from our data without having to know what is the underlying v, because we assume that in general we don't have access to v. So we want to use.
When you do the dynamical embedding, sliding?
Okay, so I would say here that in this case we're not. I used the dynamical embedding before, kind of like as a background. So this procedure, you don't have to do it.
But if you were to do it, you would use sliding.
If you were to do it, it would be sliding.
Okay.
Yeah, but yeah, that's a good point. So whatever I say from now on, dynamical embedding is an optional thing to do. So if this could be done, you know, even if you had full observations, you could do it just on the level of the snapshots. So we're going to use these XCI objects now to design kernels and control, you know, basically control the geometry of the data through this vector field. Okay, so this is the type of kernels that we're going to be working here. I call them cone kernels because their main property is that they tend to they will assign strong similarity to pairs of data points which are mutually aligned with the dynamical flow. So let's see how that happens precisely. So we have, so this family of kernels depends on two parameters. So there's one is the sampling interval. So this sampling interval in this case will play the role of epsilon in the isotropic Gaussian kernels used in, you know, machine learning. So this will be our asymptotic parameter that we are going to let go to 0. And there is another parameter which controls the influence of this angular dependence. So here we have this omega ij is just the ordinary is the norm here is the distance of the samples, the Euclidean distance of the samples, and what we do, we modify that, you know, isotropic distance by a rescaling through the norm of Xi. So this, in some sense, we're rescaling by the magnitude of the velocity of the flow, and we are also introducing these terms which depend on the angle between the flow and the relative displacement of the samples. So whenever omega ij is parallel or anti-parallel with Xi, this correspondingly the argument here of the exponential will become smaller. So we're going to put more similarity on these points. And the amount that we're allowing the angular influence to play a role is controlled by this parameter zeta. So this is what the definition so far. It's just a formula that, you know, given an order sequence of data, one can apply, and, you know, you create a kernel through that. So now we want to look at what this does to the geometry, what this does to the geometry of the data set. So, okay, this slide is showing in more detail, with hopefully fewer typos, how we construct the diffusion operator from the kernel. So we start with this integral operator, which is then appropriately normalized and turned therefore into an averaging operator, and the generator of this is what we call a diffusion operator in this context. So we'll let the sampling interval go to 0, and this is our Laplace-Beltrami in some sense. And now this depends on zeta. So for different values of zeta, we're going to get different diffusion operators. And one way, you know, I had the formula earlier with the divergence and the gradient, which is kind of like the standard formula for Laplace-Beltrami. An equivalent way of thinking about the connection with the geometry is through the decomposition of the diffusion operator into the exterior derivative and the co-differential, and there the dependence, you know, the pairing of the diffusion operator with a given metric. In this case, I'm denoting the metric by h because it will be different from the ordinary Riemannian induced metric that we had before. So the correspondence comes through the Hodge, you know, the Hodge inner products between differential forms. So working with delta, is tantamount to having induced a metric H on our data. So we want to study what that metric is. So and so this is the formula for the metric. One can check that if the finite different accuracy of the approximation is of sufficiently high order, what we're doing, we are creating a metric on the data which differs from G in two ways. On the one hand, we have this rescaling, so this is a conformal transformation of the metric G by the norm of our dynamical vector field with respect to G. So we're doing a conformal change. But in addition to that, we are doing for zeta greater than 0, we have this term which depends on the dual vector associated with our dynamical vector field. So here we are modifying G non-conformally by this term. So this is the metric that we get. I just I don't know why. Oh no. So this is just to say a couple of words. I mean, this derivation basically, as I mentioned earlier, looks at the Hessian of the kernel. So we're doing a second-order Taylor expansion in an exponential neighborhood at a given base point, and then we perform a change of coordinates to basically revert back to anisotropic Gaussian kernel and use the results of Koifman and Lafon and Belkin and Nyogi to make the connection with the corresponding diffusion operator. But what we have achieved here is that we have at least a direct way of modifying the geometry of our data with the dynamical vector field. So we want to now look at what are the properties of this new metric. So on the one hand, we introduce a conformal invariance of our metric, meaning that if we have equivalent classes of datasets which are related by conformal transformations, then the results of data analysis that we obtain using this kernel will be asymptotically, at least as delta t goes to 0, will be invariant. So so this is nice. I mean, we like to have a wide as possible class of invariance properties whenever we do data analysis, because we could be looking at data sets that contain the same amount, the similar information, and they're just different observation functions which could be non-linearly related. But other qualitative features here is what we're doing is we're contracting distances at states which have large uncharacteristically large value of the phase space flow, the magnitude of the phase space flow. So this is we're rescaling by this factor, and also what we are doing, we're contracting distances which are aligned along the dynamical flow. So whenever zeta is positive, we are compared to the original, if we take a tangent vector on our manifold, the norm of that vector with respect to h will be smaller than what it would have been normally. And in particular, when we let zeta go to 0, the metric becomes degenerate, meaning that it vanishes. If its action on every tangent vector u vanishes whenever it operates also on v, so on our dynamical vector field. So this limit is the limit that we're going to be mainly interested in earlier applications. In this Galerkin reduced model, we had found that this conformal factor was key in getting a reduced basis that was able to generate this chaotic regime transitions. We don't have a theoretical understanding of why that's the case, so it's still an open question. But what I would like to focus more about here is what happens when we let this zeta parameter go to 1. So one can now do an additional asymptotic expansion, and this time not in terms of the sampling interval parameter, but yes, 5? Okay. Okay, so I extremely overrun time, but okay, I will try to be quick. So the one can do now a second asymptotic expansion now with respect to zeta when zeta approaches 1, and derive what is the associated codifferential operator with respect to this H metric. So what happens here is that we get a formula for the codifferential operator and the corresponding Laplacian, where the dynamical vector field enters explicitly. So here, in a standard diffusion operator or Laplace-Beltrami operator, we would have the gradient of a function with respect to a given metric. Here we have the directional derivative with respect to a vector field, and this quantity here is metric independent. So this doesn't depend on the embedding in any way. So the only dependence of this object on the embedding, so our observation function of the data, is through this volume form. So this is a rescaled volume form by the norm of the dynamical vector field raised to the power m, where m is the dimension of the manifold. So all transformations of the data that leave this ratio invariant will lead to the same limiting operator. So this includes conformal transformations, but is also more general than conformal transformations. And so intuitively, what is happening here, we are creating, we are favoring diffusions along the vector field, because we are contracting distances along the vector field, but this can be made more precise. So there is a definition of what it means for a diffusion operator to act along a distribution, so in this case along a vector field, and this has to do with the corresponding codifferential operator annihilating a space of differential forms, the forms basically that return 0 when they act on the vector field. And the diffusion operator we constructed has this property asymptotically as the zeta parameter goes to 1. So this fits within the intuitive picture that we are generating diffusions along the integral curves. And if we look in particular at the Dirichlet form associated with this diffusion operator, we see that it will penalize, it will put a lot of energy on functions which vary strongly along the vector field. So in other words, functions with low Dirichlet energy are going to be those that we expect them to vary predominantly transversely to the dynamical vector field. And in particular, if we want to use eigenfunctions of this operator for various data analysis purposes, this could be, creating low-dimensional representations, or in the applications that I won't have time to show, doing, extracting spatiotemporal patterns. So we would expect that these eigenfunctions to have this property to vary predominantly in directions transverse to the dynamical flow. So I will skip. Okay, this part I will skip. It's looking at how the discrete operators are constructed from kernels, but I'm happy to talk about it offline. Here I just want to show what happens when we apply this framework to toy dynamical, to a set of dynamical systems on the torus, which we can solve analytically. So these are the formula for the vector field are shown here. They have a parameter beta that controls how it basically modifies the velocity such that at some regions of the torus the system evolves more slowly, in others it evolves more rapidly, and there is a frequency parameter which, if set to an irrational number, ensures that the flow is the torus is covered densely, but also can create different configurations of this trajectory. So we want to see how our kernels are behaving in such in these two cases. But also we're going to look at how, if we deform the torus by a non-conformal transformation, we want to see what is the impact of this deformation on the results. So what I'm showing in this picture here is scatter plots of various diffusion eigenfunctions for three cases. So in the first case, this is the isotropic Gaussian kernel. This is applying the standard diffusion map algorithm on this data set. So you can see here that the eigenfunctions partition the torus into smaller and smaller length scales, but as guaranteed basically by construction, they do not see, they are invariant as to how the data was sampled in this case. They do not depend on the trajectories in any way. In the case with zeta equals 0, this was the conformally rescaled kernel. You see that basically the eigenfunctions have finer resolution in some sense in the points where the system is evolving more slowly and we have more samples, and the phase space velocity is smaller. And in the case with this cone kernel, you can see that the eigenfunctions now have this along the vector field property, namely that they vary predominantly transversely to the integral curves and vary weakly along the integral curves. So these are giving a set of basis functions that tries to be adapted to this flow as much as it can in the sense of both the direction and the magnitude. And likewise, if we consider the other case with a different frequency parameter, it remains the case that the eigenfunctions in this case have this stripe pattern again along the integral curves, whereas, for example, with a standard isotropic kernel, you get the same results as before. And finally, I want to show what happens with this non-conformally deformed data set. Here you can see that in these two cases, obviously there are very big differences in the diffusion eigenfunctions, whereas here the qualitative nature of this along V property is indeed, as expected from the asymptotics, is metric independent and therefore applies even in these deformed data sets. So I will stop here. I'll just I'll say one word about applying this to more comprehensive model that basically you can get fewer eigenfunctions needing to capture the salient features of variability in this SST example that we tried, fewer eigenfunctions and also with better timescale separation. So I don't have time to talk about that. I will leave it here, this conclusion slide, and this is a paper that discusses this in more detail. Thank you and sorry for running over time.
We even have time for questions.
The question is, how does this compare to MSSA?
To SSA. So SSA is doing, so the comparison with SSA would be for the introductory part of the talk with the time delay embedding. So SSA or MSSA is doing effectively PCA in embedding space. So you Takens delay. So you basically have a covariance operator and you're looking again at the eigenfunction of the covariance operator. Here we're replacing the covariance operator by the diffusion operator. So that's.
But I mean, with MSSA, you can find physical meaningful quantities like etc.
Right. So here, what?
Etc. So these physical quantities come out with MSSA.
Yeah. So some of the, I mean, in some, in some of the like leading eigenfunctions or modes obtained by these methods, they tend to look alike. But other features of the data tend to be mixed together by the covariance approach. I just, to cite an example from climate science, we have a work with my student on reemergence phenomena of SST and I. So these are what people have observed is that you have this year-to-year reemergence of certain correlation structures with CIs and SST, and they have proposed some mechanism for that. So this type of phenomena, which are not, they're not associated with high variance necessarily, are very poorly represented in the SSA basis, but in fact we found that with the diffusion eigenfunction basis you can have very nice kind of like low dimensional descriptions, like basis functions for this type of phenomena. And also there were very big differences on this Charny-Devore case and Galerkin reduction.
Sorry.
I think I missed one part in the second stage of your talk. How much of this, the vector field V, is this something you have to know? I mean,
No, that's the.
you-
So you assume that it's there, it exists,
okay, but
but you don't have to know it.
you're just following the
This is basically,
observed trajectory, whatever.
yeah, it's just following the. If you have, what you have to have is of course timestamps. You have to know and then
To be ordered, but you don't know what the dynamics is.
yeah, you don't know the dynamics. What you can do is you can construct these finite differences, and this finite difference will approximate the dynamics.
Andrew?
You mentioned PCA at the beginning. One of my understanding of why that doesn't work is that low energy variables can mediate transitions that are important for understanding the
Yes.
dynamics. Can you explain why your method overcomes that?
No,
Yeah.
no, I cannot. I mean,
Not even heuristically. I don't mean theorem. I mean, is there some intuition?
I mean, I'm in this, for example, if I go, the one case that I guess most closely relates to your question is when we try to do dimensional reduction of the Charny-Devore model, where there you had, presumably there were some low energy states that by doing projection on the EOF basis you probably lost. So, I mean, if I'm trying to say something meaningful here, that it's so if you did PCA on a data set, let's say like this one, right? What you do is just introduce a cut through the torus in depending on the whatever covariance principal axis you computed. So here, on the other hand, when you and then to create the corresponding EOF, or what the corresponding PCA mode, you would project basically your data onto that cut. And here what we're doing, on the other hand, instead of projecting along cuts, we are trying to follow, in some sense, through this using these eigenfunctions as convolution filters, trying to follow what the trajectories are doing. I know that this is very vague, and why that will guarantee you to get the better Galerkin reduced model, unfortunately, I don't have a lot of intuition. But
So there's dynamical information going in there, but these items they're not changing over time.
no, they're not changing over time, but in this sense, this manifold is not changing over time either. I mean, the system is just going through this. Going through this, through these trajectories, through this manifold.
Okay.
I have a quick question. Typically, in the previous, when you do these diffusion maps, as you explained, I mean, the value of epsilon that you pick is always a bit mysterious.
Yes.
And it depends on the amount of data that you have.
Yes.
Here, I don't see how you. I mean, is this value of this? See there parameter? Where does the?
So for the asymptotics, okay, let me pull up the formula here. So, sorry. So for the asymptotics, this xi here, which scales like delta t, and as delta t plays in this case the role of epsilon, meaning that as you collect finer and finer samples in time, it's as if epsilon.
Okay, so it sees immediately the amount of data that you have.
Yes. So however, it's not a panacea, so to speak, meaning that in practical applications, it might be a good idea to stick in an epsilon here anyway, and allow you to tune it a little bit. But the tuning is not going to be. It's going to be of order 1, let's say. You're going to nominally choose. If you put an epsilon here, you would nominally say epsilon is equal to 1, and then if you don't have really control on how let's say you are observing data from satellites and you don't really have control, you might help you to put an epsilon here and tune it a little bit.
Isn't it worse than not having control? I mean, suppose you want to look at large-scale climate dynamics.
Mm-hmm.
So suppose you start by doing what you did in the beginning. So you've got, say, SST maps,
Yes.
a bunch of 20 years of satellite SST maps.
Yes.
And I guess I somehow, and so you say, okay, what I'm going to do, because I don't want to take the annual cycle out because I get in big trouble if I do that, so I take them in 20 years. Instead of having 20 times 365 for daily data, I stack up years and now I have 20 of them. And then playing this game is going to be awfully difficult. For one thing, I can't say epsilon equals a year and say what happens when a year shrinks to 0.
Well, this is for the asymptotics. I mean, you can always. So if the epsilon goes to 0, is to gain an understanding of what this kernel does to the geometry of the data. Had you been able to sample it arbitrarily?
What do I do if I have the data sets that actually are?
Well, you basically what I skipped through in the talk, which is that you can do your asymptotics, and of course you're not going to be in the asymptotic limit. I'm not pretending that this is the case, but what you can make, basically you can draw a theory which is basically completely follows what you get from in the epsilon equals 0 case, but for discrete data, and construct all these corresponding operators in the discrete setting, and apply it. And what you're doing is you're using the intuition that you gained from the continuum limit to design these kernels, but then you're going to apply it away from the asymptotic limit, and then you hope for the best. I mean, you do not have any guarantees, but if there are certain structures in your data which are visible to this kernel at epsilon not 0, you're going to pick them up mean,
I was kind of hoping that the kernels would make things visible that weren't apparent in the beginning.
well, I mean, that's what I mean. I mean, this structure, this is what this is trying to do in some sense.
Perhaps you should continue the discussion offline at lunch. I mean, the exam to show. Okay.
Okay.
Thank you.